So just quickly review what we did last time. So I defined this simple notion of a chain complex, which is a sequence of vector spaces and linear maps such that two of them give you 0. The spaces are called the chains. The null spaces are the cycles. That contains the ranges are the boundaries, and the quotient is a homology space. And then we did an example, which is a simplicial chain complex. You take a simplicial complex, and the chains are formal linear combinations of the simplices of each dimension, and the boundary operator is, in fact, take the boundary of a chain to get a lower dimensional chain. And that gives you the simplicial chain complex. So each of the vector spaces is finite dimensional, namely this is the number of triangles, and this is the number of edges down to the number of vertices. And the homology gives you the Betti numbers that tells you the number of holes of different dimensions in the domain. And then the last thing I mentioned, which I rushed through a little bit, was the definition of a chain map. So you have a chain complex, and you have another chain complex, and you have a graded vector space map of degree 0. So it maps vk into the v prime k. It doesn't change grades anymore, in such a way that it commutes. And the reason that's a valuable notion is if that happens, then it induces a map on the homology of the top complex to the homology of the bottom complex. And that map is functorial. That is, if you have the composition of two of them, then you get the composition of the induced maps. And an implication that comes right away from that is if this map is a projection, which means it leaves, if v prime k is a subspace of vk, and f leaves a subspace invariant, then the induced map at least is a surjection on homology. That's where we were. Any questions? Okay, now I want to, now I'm going to make the simplest possible modification of the definition of a chain complex. A cochain complex is exactly the same thing, except instead of the indices going down, k, k minus 1, k minus 2, they go up, k minus 1, k, k plus 1. Okay, so it's obviously the exact same concept. The interesting thing will be sometimes when there's a chain complex, there's another cochain complex running around. The correct terminology, instead of calling them chains and cycles and boundaries and homology, they call them cochains, cocycles, coboundaries, and cohomology. But then they often leave that off and don't bother. So, and the convention is when you write cochain complexes, use superscripts, while chain complexes, they're usually subscripts. So the cocycles are z super k. And one nice way to get a cochain complex, if you start with a chain complex, is to take the dual. So of course, whenever you have a linear operator from one vector space to another, this is now a single vector space, then you have the dual operator that goes from the dual space of W back to the dual space of V, of course defined by L star of some W star, is supposed to be an element of V star, so it acts on a V, where V is in V, and it acts on it by W star acting on L of V. So if we have a chain complex, Cn goes to Cn minus 1 goes to so forth down to C0. And we have boundary operators here. By the way, one often leaves off the subscripts. For now, I'll put them in here. Then we can say, take the dual of this operator, and so here we get Cn minus 1 star and Cn star, and we get an operator that goes back this way, which is dn star. And now the indices go, now the indices are going up, so this is a cochain complex. That is, it's a cochain complex if we define this to be V, if we define Vk to be Ck star, and we define this should be V super K. d super k to be, I guess it's d sub k minus 1 star. It's the, no, it's the other way around. D super k minus 1 is dk star, right? This would be d super n minus 1, because it starts at the n minus 1 guy. It's dn star. Okay, so that's a cochain complex. And let me give you an example of a cochain complex. And I don't want to give you a trivial example like just re-index the simplicial chain complex, but quite a different one, the de Rham complex. So this will be a key object of study for us. So let's start in 1D. The de Rham complex is pretty simple. It only has two spaces. We index one of the spaces with 1, and the second space with with 0 and with 1. It's a cochain complex, so we're going up. The 0 space, the 0 cochains are just functions. Omega is an interval in one dimension. So omega is an interval. We take all C infinity functions on that interval for both spaces. And the map between them is the derivative operator. And all the other spaces are 0. If you only have two spaces, everything else is 0. It's definitely a chain complex. All the compositions are certainly 0. Not very interesting. Although it already has some information, you could ask, what's the cohomology at the 0 point? The null space is everything whose derivative is 0, so the constants. And the range is 0, so constants mod 0 is constants. So the homology is the constants. So that's because an interval has one connected component. There's some information in there. 2D is more interesting. We start with smooth functions on a two-dimensional domain. We take their gradients and we get smooth vector fields. And we take the rotation. By the rotation, I mean the scalar valued curl. I guess we've seen it before. Rotation of U1, U2 is minus D1, U2 plus D2, U1. And the rotation of a gradient is 0. So this forms a complex. In 3D, we start with the gradient to vector fields, and then we take the curl, and we get vector fields again, and then we take the divergence. And the curl of the gradient is 0, and the divergence of the curl is 0. So this is a complex. And we'll get to the ND analog of this in some detail later in the course, but I'll just mention that the space of C infinity functions can be done on any domain, and those are called the 0 forms, and I denote it lambda 0 of omega. And then the gradient operator is the first exterior derivative, and this lambda 1 of omega is something like vector fields. And then this is something like a curl, but it goes into a different kind of thing, and so forth. The last one is something like a div. So that's the de Rham complex in ND, but if you're not comfortable with that for the moment, just think about this very concrete thing in 3D. But as I say, it can be generalized to n dimensions, and we have a space lambda k of omega, which is differential forms of degree k. This is smooth differential k forms. And we have a derivative operator, which depending on the level is like a gradient or a curl or something, which takes a k form to a k plus 1 form, and always satisfies d followed by d is equal to 0. So we get a cochain complex. Okay, and the other thing we need from the theory of differential forms is that there is a notion of integration of a differential form over a simplex. And it has to be the case where the differential form is a k form and the simplex is k-dimensional. Those k's have to be the same. So 0 forms, things here, can be integrated over points. That means they can be evaluated at points. So the integration operation for the 0 forms is just take a function evaluated at a point. 1 forms, which are these vector fields, they can be evaluated over an edge, and the meaning of this integral, so if V is a 1 form and F is one-dimensional, then the meaning of the integral of f over v is our usual integral of v dot the tangent vector to f, the line integral from the beginning of f, if f goes from a to b and is oriented in that way from a to b, over f. And in a similar way, there's a way to integrate a differential k-form over a k-dimensional either surface or a simplex. And it's defined in such a way that Stokes' theorem holds. So Stokes' theorem in this context can be written as the integral over a k-dimensional simplex or a k-dimensional chain of the derivative of a k minus 1 form. Oh, yeah. There's an error here. That's a k minus 1 dimensional form. So du is a k-dimensional form and can be integrated over a k-dimensional chain. So let me write this down over here. Okay, so if u is a differential k minus 1 form, and C is a k-dimensional chain, then du is a k form, and the integral of a k form over a k chain makes sense. The boundary of C is a k minus 1 chain, and the integral of a k minus 1 form over a k minus 1 chain makes sense. If you're really careful here, you would write the trace, because this is not the full, this is the restriction of the form to the boundary. And these things are equal, that's Stokes' theorem. Okay, as I say, we'll do this in much more detail, but now I'm just summarizing the main results from exterior calculus. And one of the most important things about exterior calculus, it's a way to define a derivative and an integral that works on any smooth manifold. But here we're just talking about a domain in Rn. Okay, any questions? Well, the only purpose it serves is that we want to be able to define the cohomology at this level. By definition, it's the null space of this map. That's the zero map, so the null space is the whole space, divided by the range of the div map. So here, it's the co-kernel of the range of the divergence. It's C infinity omega minus, modded out by div of this. If I didn't have the zero here, you wouldn't have the cycles. So all this is saying is that every chain is a cycle on this end. And here it's saying no chain is a boundary on this end. Only the zero chain is a boundary on this edge. That's all it means. Any other questions? Yeah.
Some authors used to either precede these complexes with real numbers, and which denotes inclusion of constants, and some postpone put at the end the real numbers, and which is postpones the integration of.
So you do that. So let's take as an example a simplicial chain complex in 2D. So you have 2 chains and 1 chains and 0 chains, and everything else is 0. And suppose the domain is simply connected. That's being triangulated. So no holes. So then what are the Betti numbers? What's the dimension of the homology? Here it's 1 because there's one connected component. Here it's 1 because there's one connected component. Here it's 0 because there's no holes. And here it's 0 because any two-dimensional domain has a 0 Betti number. sometimes what people say is they put the real numbers here, and so this is the constant map that sends every vertex to 1 here. And now, let's see, is that right? No, this is, let's see, this is, what would this map be? Oh, you take some, let's see, you take, what would this map be? C0. This map must be, yeah, it must be what I said. You take every vertex equal to 1. And so that if you have the boundary of some simplex, the boundary of that would be the difference between 2 vertices. So it would go to 0. So this would still be a complex. And this complex would now be exact. It would have no cohomology here because the kernel of this is the range of this. Before, we didn't have, before the kernel was everything, and now the kernel is only things where they don't add up to 0. So then this extended sequence, where you sort of have something in the -1 position, is exact. And so it's useful oftentimes to put this on the end and say we have an exact sequence. But that's no more information than to say we have this sequence, and it's exact except for there's homology that's equal to the real numbers at one end. So they stick the real numbers at one end or the other because oftentimes that's the only non-zero homology. Any other questions? Okay, so now let's talk about this Durham complex that's here, and what's that good for? It's very different than our simplicial chain complex because now the vector spaces are infinite dimensional function spaces rather than finite dimensional vector spaces. And there's an interesting chain map that connects the Durham complex, which is a cochain complex, to the simplicial cochain complex. A chain map would have to take a cochain complex to a cochain complex, both indices going down or both going up. And so we had the simplicial complex, C, which is a chain complex going down. So this is the simplicial chain complex. And then if we dualize it, so we get, I'm going to dualize it, but instead of writing going to the left, I'll write it going to the right. So we have 0 goes to C0 star, goes to C1 star, goes to Cn star, goes to 0. These were the boundary operators. These are the duals to the boundary operators. So that's the simplicial cochain complex. And of course, it has basically the same information. The homology classes are just the duals of each other, so they have the same dimensions and so forth. So now I'm going to create a chain map, or not I'm going to create, Georges Durham created a chain map from the Durham complex, which is the differential forms, to the simplicial cochain complex. So let's put the Durham complex up here. So that 0 goes to 0 differential forms, goes by the exterior derivative to 1 differential forms, goes to n differential forms. So that's the Durham complex. Yeah, Jill told me not to use the squeaky ones. And here we have the simplicial chain complex. Okay, and now we want to create a map down here. And we want it to commute. Okay, so we want to have a map that takes, let's start here, takes a C infinity function and gives you something in the dual of the space of zero chains. Okay, so the dual of a zero chain means it gives you a function that acts on zero chains, and zero chains are just linear combinations of vertices, so it gives you a function on the vertices. So I have a function, I want a function on the vertices. Well, I just apply my function to the vertices, I just restrict it. So here the mapping would take a C infinity function, and it would go down to U restricted to the vertices. The next one's a little more interesting. Here I have a 1 form, and I want it to act on edges. 1 chains are linear combinations of edges. Okay, well, I can, a 1 form acts on an edge because I can integrate it on the edge. The integral of a 1 form on a one-dimensional edge makes sense, or in general, the integral of a K form on a K-dimensional simplex makes sense. So this map going down in, this would be, U goes to the thing that takes an edge F to the integral of U on F. This is a dual of a chain, it's a cochain. And this is a K form. So I have a map from here to here. So, and the general thing is if I have a K form, then I get something that acts on K-dimensional chains by integrating the K form over the K chain. That's de Rham's map. And so here it is. You have a K-dimensional differential form of the K form, and you're going to have something which is in the dual of K chains, namely the integration of U over the chain. Now, I said that that was a chain map, so that's saying that if you apply the de Rham map to D of something, you get the same thing as if you take the dual of the boundary operator applied to the de Rham map of the thing. Okay, write down what that means. So you need to know the definition of the de Rham map, and you need to know the definition of the dual of a linear operator. Just write it down and read what you got. You just wrote down Stokes' theorem. You wrote down this. This is exactly the statement that the de Rham map is a cochain map. So take that as an exercise if you haven't seen it before. So now we have the de Rham complex up here with the exterior derivative, starting with smooth functions and smooth vector fields and so on. And then we have the cochain map with the duals of the boundary operators. And we have a mapping from this complex to this complex, which commutes. So it creates a mapping on homology, on cohomology. And de Rham's theorem says that this map is an isomorphism on cohomology. So we have two very different complexes. This is finite dimensional spaces created with triangulations, and this is something with PDEs and differential forms, but they have the exact same cohomology. So in other words, the dimension of the cohomology spaces for the de Rham map are these same Betti numbers. That's de Rham's theorem. And actually, it can be proven using the finite element tools, and maybe I'll be able to prove it at the end of the lectures, towards the end. So what's the idea behind it? How can you tell if a domain has a hole by looking at PDEs? That's what this is saying, that by looking at whether some PDEs have kernels and ranges, you can tell how many holes a domain has. Well, here was the example we saw before where we did a simplicial homology. Now let's do de Rham cohomology. So we have this cylinder. Well, we saw this example in a numerical example. If you take the gradient of theta, that is a cycle. That is to say, the curl of that cycle is 0. Let me put up the complex we're talking about here. Let me do it in 3D, say. So the de Rham complex in 3D is C infinity functions. Take the gradient and get C infinity vector fields. Take the curl and get C infinity vector fields again. And take the divergence and get functions again. And what I want to show you is because there's a hole, there's a function in here that goes to 0 under curl, but which is not the gradient of a function in here. And the function I'm going to take is this u is equal to grad of theta. Now theta, of course, is not singly defined. When you go around the loop one time, it increases by 2 pi, but grad theta makes perfect sense and gives you that field. Since locally this thing is a gradient of a uniquely defined function, curl of this is equal to 0. But there's no C infinity function for which u is a gradient. Because if it was, it would just be theta plus a constant, and that theta plus a constant is theta has a discontinuity when you go all the way around. So because of that hole, there exists a function that's defined like this that is a cycle but not a boundary. So there exists homology. That's what Durham's telling you. What about the second level? Here, the existence of something that's in the null space of divergence but is not a curl should say there's a void inside the domain. So the example here, take a sphere that has a little sphere in the inside cut out, so a spherical shell. I always have trouble drawing it, so just a hollow sphere, right? So it's that domain, if you spin it around the axis, take the solid of revolution. Take that vector field that's shown in there, spun around. That's the gradient of 1 over r. Because we have a hole in our domain where the origin is, 1 over r is a nice smooth function, and grad 1 over r is a nice smooth vector field. So we take this u is equal to grad 1 over r. What happens if you take the divergence of this? Well, that's the Laplacian of 1 over r. 1 over r is the fundamental solution of the Laplacian. Its Laplacian is 0 everywhere except at the origin where it's undefined. So this is equal to 0 in our domain. So that's a cycle, a cocycle. Its divergence is 0. Is it a curl of anything? Well, it's not a curl of anything. And maybe that's a little exercise. Show that the integral of curl of any smooth function dotted with grad 1 over r over this spherical shell, this is equal to 0. Integration by parts in the boundary conditions. So this is orthogonal to curl, so it can't be a curl itself. So there exists a function. If you have a hole in your domain, you can create a function like that, at least I've shown in a specific example, which has non-zero cohomology. It's a cycle, cocycle, but it's not a coboundary. That's the heart of Durham cohomology. Totally different way to measure holes. But it gives you the same answer because of Durham's theorem, which says that you get the same cohomology from both approaches. Okay? Okay, that's the end of Homology 101. So we have the basic definitions, the chain map and induced map on homology, and the two examples of simplicial complex and simplicial chain complex, and Durham cochain complex, and the Durham theorem connecting them.
How about n equal to 4? Can you write the Durham sequence?
So what the Durham sequence would be in n equals 4 would be you start with C infinity functions. You take the gradient, and then you have C infinity vector fields. And now you take what I would call the curl in R4, which is the skew symmetric part of the gradient. So you have a vector field, you take its gradient, that's a matrix, and you take the skew part of that matrix. So the components of it are diuj minus djui. That's a sort of four-dimensional curl, but it doesn't give you either a scalar or a vector. It gives you a skew matrix field. So it would be C infinity into omega into R 4 by 4 skew matrices. Then there's another operator here. And, well, the answer is that this one goes into C infinity R 4 by 4 by 4 skew third-order tensor fields. It's now getting a little bit harder to think about, but this space actually has dimension 6. This space also has dimension 6. So we'll get to this. And they run out of names for these, so we start just calling them all D. And then the last one, no, this is 4. And then the last one, well, this is, since it's 4, it's isomorphic to R4. If you put it in the right order, it's just the divergence, and it gets you back to functions. And so these are 0 forms, and 1 forms are like vector fields, and 2 forms are skew matrix fields, and 3 forms, or n-1 forms in n dimension are like vector fields again, and n forms are like functions. Actually, at every step, you take the gradient, but that gets you a tensor with one more index. So first you have scalars, then vectors u sub I, then matrices uij. You always get it by taking the gradient of all components, but then doing the skew symmetrization operation.
What's the magic of skew symmetry?
I'm not sure I want to go there. It's a little complicated to explain, but I'm going to give you an exercise to think about. These concepts carry over to an arbitrary smooth manifold. You do not have to have a measure or even a metric in your space to define these. They're independent of the choice of a metric or a measure. That's true for the skew symmetric part of the gradient. It's not true for the symmetric part of the gradient. Symmetric part of the gradient is the operator that enters elasticity, and it measures change in metric, and it's very metric dependent. But the skew symmetric part turns out to be metric independent. So that's part of the answer. Okay, that closes this chapter, and so... This one or this one? Well, so the exact formula in Rn, not on a general manifold, these are functions u. This goes to diu, which gives you a vector field, say, v, I. Then this one goes to di vj minus dj vi, and this gives you a skew matrix field, wij. And this would go to di wjk plus dj wki, and there's 6 combinations, 3 with plus signs and 3 with minus signs. Take all 6 permutations of ijk here. So you get the skew symmetric part of the gradient. That would be the one in here. And that pattern just continues. What is it physically? Well, that's a hard question. What's the curl physically? Vorticity or something? I mean, they arise in various cases. I think this operator probably plays a role in relativity, but of course it's a little harder to get physical already in 4 dimensions and above than it is in 3. Okay, so I need to start the next chapter, which is another tool. So we drop homological algebra. We'll come back to it later. And now I want to talk about unbounded operators in Hilbert space. So this is a pretty standard topic, and there are many good books on it. For example, Yoshida's functional analysis has plenty on this subject. There's quite a bit in Cato, some of the more modern books. But it seems to have been more popular in the past than it is recently. So if you take an average course on Hilbert spaces, you think that all subspaces of any importance are closed and all operators of any importance are bounded. But this goes a little bit beyond that. And there's a lot of definitions, and here there's also some theorems. So maybe I'll try this thing here. So we have two Hilbert spaces, X and Y. And all this stuff can be done in Banach spaces, but sometimes the proofs are more complicated and even topological vector spaces. And now what we have is a linear operator T, but it doesn't map the whole space X to Y, just a subspace, which we call the domain of T, dt, into Y, but it is linear. It's not, the subspace dt is not necessarily closed, and the operator T is not necessarily bounded. Of course, the case where dt is all of X is included. The case where T is bounded is included, so that's unfortunate because it means that bounded operators are unbounded operators, which is a bad terminology, but I don't want to call them not necessarily everywhere defined and not necessarily bounded linear operators. But that's what they are. And we're going to have two key properties of such operators. One is densely defined, and the other, which we'll get to in the next slide, is closed. So densely defined means that the domain is dense. If your operator is not densely defined, you probably took the wrong X. Probably should take its closure of dt instead of X. And so let's have a typical example, and this is the one to keep in mind in the beginning. X will be L2, and Y will be L2 vector fields. And the operator will take a function to its gradient, and that's defined for anything in H1. So if V is in H1, then its gradient of V is in L2, so it's in Y, so I can define it. Okay? That's a densely defined unbounded operator because H1 is dense in L2. The choice of the H1 as the domain, there's many choices that could have worked. Or I would need the domain to be inside H1 so that the gradient is in L2. It could have been H01. It could have been C infinity. Could have been C1. Those are all possible choices. And each one gives a different unbounded operator because the unbounded operator is both the operator and the domain are part of it. Okay, doing arithmetic, well, if you have two operators and you want to add them or multiply them or something like that, the operator is the obvious thing. It's S of X plus T of X. But the domain is only the place where both of them make sense. And you have to be a little careful because if you use something like that, you can't assume it's densely defined just because S and T are densely defined. That might or might not happen. And compositions is something similar. If S takes X to Y and T takes Y to Z, then T composed with S is only defined on the domain of S, those things in the domain of S, such that S of V is in the domain of T, and then T composed with S makes sense. And a few more definitions. There's the graph norm of, so there's a way to put a norm on dt. So we have T is going from dt to, which is part of X, into Y. And there's a way to put a norm on dt, namely the norm of some X in dt is just the norm of X in X plus the norm of Tx in Y. And since we want to keep the Hilbert property, I'll put squares everywhere. And then it comes from an inner product, which you can surely guess. X z in dt inner product is xz in X inner product plus Tx tz in Y inner product for X and Z in the domain of T. Let's see, the null space is defined in the obvious way. The null space is those things in the domain of T that T maps to 0. The range is defined in the obvious way. It's the image of the domain of T under the mapping T. And the graph is defined in the obvious way. The graph of T is the set of X comma T of X such that X is in the domain of T. And that's contained in X cross Y. And it's a subspace. And T is actually one-to-one onto map from dt. Sorry, not T. We have a map from dt to the graph of T, which is the obvious map that X goes to X comma T of X. One-to-one and onto. Okay, all simple definitions. Oh, I see. So now I have to clean up my board here. Let's see if this works. No? Let's try that again. Ha! Okay, so this is the important definition. This restricts the operators a lot. It's a condition that's weaker than being bounded, but for which many of the properties of bounded operators carry over, and that's called closed. So an unbounded operator is called closed if its graph is closed in x cross y. So what does that mean? Well, that means if we have a sequence of points, v1 vi tvi, or vn tvn, in the graph, that means that the v's are in the domain of t. And if they converge to some xy in xy, so that means vn converges to x and tvn converges to y, if those two things happen, then it has to be that xy is in the graph, so x is in the domain of t, and tx is equal to y. So this first statement, t is closed, if that holds, and this equivalent definition are just the definition of the graph and being closed. And then the second definition is also equivalent. So the graph is a subspace of x cross y. So it's closed if and only if it's complete. And the graph in the x cross y norm is the same, is isomorphic to dt in the graph norm by this one-to-one onto map. So also completely equivalent is to say that dt with the graph norm is a complete space. Now you see why we deal with unbounded operators. Because if you have not everywhere defined operators. Because if you have a closed operator which is defined everywhere, then it turns out to be a bounded operator. So the statement is if you have a linear operator that's defined everywhere and its graph is closed, then it's a bounded operator. That statement is the closed graph theorem that's in every book on Hilbert space. Okay, and many of the properties of bounded operators extend to closed operators, especially because you have this dt, which is a nice complete Hilbert space by itself. So here's one. Maybe the first one I'll go through and I'll write out the proof. You have a closed operator from x to y, then its null space is closed. So t closed, x to y. Then the null space of t is closed in y. So that means if I take a bunch of v's in the null space of t, that means they're in the domain of t, and tvn is equal to 0. And we want to show that this is a closed set. So suppose the vn converges to some v. We want to show the v is in the null space of t. Well, the vn is converging to v, and the tvn is 0, so that's converging to 0. The definition of closed says that this means that v is in the domain of t, and tv is equal to 0. It's the definition of closed. You have the v's converging and the tv is converging, then the limit is in the domain, and t of the limit is the limit of the t's. So that implies that the limit of things in the null space is in the null space. That's the kind of proofs you have a lot with closed operators. I think I won't give all the details of these other ones, so these are good exercises also, and if you have any problems, I can certainly discuss them. Let's look at this one. First of all, let's think of the case of a bounded operator. So probably many of you know the characterization. If we have an operator t, which is coercive in this sense, tx in norm is bigger than a positive constant times x in norm, well, that operator is obviously one-to-one. T can't be 0 if x is 0. And it has a closed range. And in fact, an operator is one-to-one with closed range if and only if this inequality holds. That's for bounded operators. And that carries over to closed operators very easily. Basically, think of t acting on the domain of t with the graph norm and apply the usual theorem. And so an operator is one-to-one with closed range if and only if it satisfies this inequality. Yet another property, again, you may or may not know this for bounded operators. If you have a bounded operator whose range is almost the whole space, the dimension of the quotient, the codimension of the range is finite, then the range is closed. Remember, not all finite codimensional spaces are closed in a Hilbert space, but if it's a range of a bounded operator, it's true. And it's also true if it's a range of a closed operator. And the reason is because a closed operator, if you think of it as acting on the domain with the graph norm, it's a bounded operator, and so you can apply the usual theorem. Okay, that gives you some examples of how you carry things over from bounded operators to closed operators. So now get to a very important concept, which is adjoint. And to define adjoints of operators, they should be densely defined. So the key hypothesis for defining adjoints is that it's densely defined. It doesn't have to be closed, the operator you're taking an adjoint of. So we take a densely defined unbounded operator T from X to Y, and I'm going to define its adjoint is going to be an unbounded operator going from Y star to X star. Sorry, from Y to X. We're in Hilbert space. So I have T is an unbounded operator from its domain, which is dense in X, to Y. And I want to define T star, and that's supposed to be an unbounded operator from its domain in Y back to X. And the domain of T star is given by that formula there. You look at those W that are in Y such that when you consider the product WTV, the inner product WTV on Y inner product, what is this? This is something that takes V in X and gives you a real number. So that's a linear functional on X, not on all of X. Sorry, it's only defined on the domain of T. Okay? So I take any W in Y. I look at the inner product of W with TV, defined for any V in the domain of T. And that's a linear functional from this dense subspace dt into R. And that might be a bounded linear functional, it might be an unbounded linear functional. And the domain of T star is a set of W and Y such that this is bounded in X norm. In other words, satisfies WTV in, that's a real number, is less than a fixed constant times V in X norm for all V in the domain of T. That's the definition of the domain of T star. And if this functional is bounded, then this is a dense space. It extends to a bounded linear functional from all of X to R. And in Hilbert space, a bounded linear functional is the inner product with something. So if W is in dt star, there must exist some Z such that WTV is equal to ZV in the X inner product by the Riesz representation theorem. Okay, if this is a bounded linear functional, it must be the inner product with something. And TZ is what we call T star of W. Depends on W. Okay, so to make a long story short, we have this equation here that for any W in the domain of T star and any V in the domain of T has to hold. And if there is a T star of W that makes this hold, then W is in the domain and T star of W is that guy. That's the definition of the adjoint. to get properties of the adjoint, well, the first thing is that T star is a closed operator, always a closed operator. So why is that? Well, suppose we had this relationship for a sequence of guys. Suppose for each Wn, we had a T star Wn with this relationship holds. And suppose that the Wn's were converging to some W, and the TWNs, T star Wn's were converging to some Q. Well, then I could pass to the limit in this, because this is converging, and I take the inner product, so I would get WTV in Y is equal to QV in X for all V in dt. For each such V, I just take the limit. And that shows that W is in the domain of T star, and T star W is Q. So whenever I have a sequence of things satisfying this, then their limit satisfies it. So T star is a closed operator. Okay, and to get to further properties, what I want to do is I want to compare the graph of T and the graph of T star. But the problem is the graph of T is in X cross Y, and the graph of T star is, of course, in Y cross X. So I fix that by switching them, and it's nice to throw in a sign off also. So I make the twisted graph of T star contained in X cross Y, and this would just be the set of things of the form X over here and Y over here, and minus T star Y here. So we're used to defining graphs where the abscissa is in the first position and the ordinate's in the second position, but we switch them around now. And the reason to do that is now I can compare them in an easy way. I get this relation here that let's check that the graph, the orthogonal complement of the graph of T is just this graph of T star twisted around. So let's check this. So we take the graph of T, orthogonal complement. So this is the set of things in X, Y, such that its inner product with anything in the graph of T is 0. Anything in the graph of T is VTV. Okay, that's just the definition of the orthogonal complement using the inner product on X cross Y. And if you look at that, that's exactly the definition of the fact that Y is in the domain of T star, and T star Y is equal to X. So this is the set of all, or actually there's a minus sign here because I bring it over with a minus sign. I put this as equal to minus. That's exactly the definition of minus T star Y comma Y, such that Y is in the domain of T star. So just from the definitions, we get that the orthogonal complement of the graph of T is the graph of T star twisted around. Okay, now let's take that relationship. The orthogonal complement of the graph of T is the graph of T star. And let's take orthogonal complements on both sides. Well, the orthogonal complement of the orthogonal complement is the closure for any subspace of anything, right? So this is the closure of the graph of T. I didn't assume T was a closed operator, so those might be different. Is equal to the twisted graph of T star, orthogonal complement. So that's the second relation I wrote there. And therefore, T is closed means that the graph of T is equal to its closure. So therefore, we have the theorem that T is closed if and only if the graph of T is the graph of T star, orthogonal complement. Okay. So that's true for any operators. Now suppose that T is not any densely defined T, Now suppose T is also itself closed. So T is closed and densely defined. Well, then we already know T star is closed, but also T star is densely defined. So how do we do that? I'm not sure if I can. Let me glance at my notes here and do it in an efficient fashion. Okay, so let me prove the first part of this, that if T is closed densely defined, then T star is not only closed, but also densely defined. So we have to show that if y is in y and y is orthogonal to the domain of T star, then y is 0. That would show that the domain of T star is dense. To show, we're trying to prove domain of T star is dense. So there's nothing except for 0 that's orthogonal to it. So y is orthogonal to D of T star. That's the same thing as saying that 0y is orthogonal to the graph. Well, the twisted graph, because what's in here, these are things of the form minus T star y comma y, where y is in the domain of T. And so when I take the inner product, the 0 gets rid of the first part, and just says y is orthogonal to the domain of T. Okay, but the orthogonal complement of the graph of T is the closure of the graph of T star. It's the closure of the graph of T, and we assume T is closed, so this is equal to the graph of T. But if 0y is in the graph of T, that means y is T of 0, so that implies y is equal to 0. Okay, so they're fairly simple ideas, although it can be a little confusing. Okay, the rest of this is pretty easy. You can easily see that if you start with a closed operator, closed densely defined operator, you take T star of it. We saw that's closed densely defined, so you can star it again. And that, if you do it, just go through the definitions, you'll get back to T itself. So T star star is equal to T. And then the most important thing is this relationship between the ranges and the null spaces of the operators. Even if the operator is closed, its range may not be closed. So you see closures of ranges here. The null space, of course, is always closed for a closed operator. So let me prove one of these. Let's prove that the null space of T is the range of T star perp. That's the second one in this column. So if I take Z in the null space of T, so then we go to the graph and say Z0 is in the graph of T. That's what it means to be in the null space. But the graph of T is the orthogonal complement, since it's a closed operator, of the twisted graph of T star. And so to say Z0 is orthogonal to the twisted graph of T star means that Z is orthogonal to T star y for all y. So that's the same as saying Z is orthogonal to T star y for all y in the domain of T, which is just to say that Z is orthogonal to the range of T star. So we have shown that the null space of T is the orthogonal complement of the range of T star. Now if I take the perp of this, I'll get the range of T star perp no perp, the closure, because I took perp of it, so I get its closure, is equal to the null space of T perp, which is the second one on the first line. And everywhere, if I replace T by T star, this becomes the null space of T star, and this becomes the range of T star star, which is just T perp, which is one of the other ones, the first one. And if I replace T by T star in the second one, I get the last one. Okay. Should be an easier way to erase this whole board. No, that's not what I want either. I need the eraser. This is hard. And finally, okay, there's a typo in this slide here. This should say the closed range theorem. And so this is a very important theorem that we'll use. It's sort of simple, proven in a similar way to the ones we've done before. As we saw, that a closed operator may not have a closed range. The closure of its range is the orthogonal complement of the null space, but it may not be closed. But it's very important when they are closed. We'll be mostly interested in closed, densely defined operators whose range is also closed. And the closed range theorem, which is different than the closed graph theorem, says if the range is closed of T, then the range of T star is closed. And let me see for a second how much I want to say about the proof of this. Well, I'll hold off, and if we have time at the end, which is coming pretty soon, I probably won't. So what I'll say for the proof of this is, first of all, it's about the same to prove for bounded operators as closed unbounded operators. And it's not very hard what you do. So you're trying to show that the range of T star is closed when the range of T is closed. First of all, you change the range. So we have so we have this operator from the domain of T contained in X to Y, and the range of this is closed. So replace Y by the range of T, which is a closed subspace of Y, and so it's a Hilbert space itself. And then think of a new operator, T tilde, which is just the restriction of the range. So T tilde goes from the domain of T, which is contained in X, domain of T to this new Hilbert space, the range of T. This is now onto, because I got rid of everything except for the range. Now, if I use the graph norm on T, this is a bounded linear map that's onto. Okay? Mod out by the kernel. Call that T tilde tilde. Now it's a one-to-one onto bounded linear map. Then you use Banach's theorem that says if you have a one-to-one bounded nonlinear map, the inverse is also a bounded operator. Then you combine that with the definition of the domain of T star, and it's not hard to see this step 3 here, that T star Y bounds Y. So I'll say some more about it if we have time, or you could try to fill this in as a not so easy exercise. And in a few lines you get that, and that condition says that T star is one-to-one with closed range. That's the T star associated with this guy, but you can easily relate that to the T star with the original T. That's the proof. Okay, and what I want to do next is an example. of some operators here. And I want to relate this to the definitions you probably know of Sobolev spaces and differential operators defined on Sobolev spaces and distributions. So think of an elementary treatment of Sobolev spaces, like would be in Evans' PD book near the beginning of the Sobolev space chapter. You take a function u in L2, and you want to say it has a weak derivative in L2. Weak gradient in L2. If there exists a vector field phi in L2 such that the integral of u dotted with the gradient, u times the divergence of any, actually I don't want to call this phi, let's call this v, of any C0 infinity test function is the same as the integral of v dotted with the function, and that would be for all phi in C0 infinity. Right, so v is a vector here, and phi is a vector test function. And this is the definition of v is the distributional gradient of u. And u has an L2 derivative, a L2 gradient, if there exists such a v, right? That's just the same as saying that we start with a closed, we start with not a closed, but with a densely defined operator minus div. Its domain is C0 infinity vector fields, which is contained in, let's do it in R3. And it goes into L2. Okay, so I think of minus div as an unbounded operator from L2 to L2, whose domain is C0 infinity. And then I take the adjoint of that, which is always a closed operator, and this is the definition of the adjoint. U is in the domain of the adjoint if there exists a v whose inner product with phi is the same as u with div phi. So u is in the domain of the adjoint is exactly the same as to saying grad u exists in L2. U has a weak derivative in L2. The distributional derivative of u is in an L2. Okay, so this definition, which you're probably familiar with Sobolev spaces, is really just the adjoint in Hilbert spaces. Okay, use this to define the grad, and so this is, of course, the definition of the Sobolev space H1. So we have now defined a gradient operator whose domain is H1. And it ends up in L2. It's just the adjoint of div on C0 infinity functions. Okay, that was the first example I gave you of a closed unbounded operator, the gradient with domain H1. It's a closed operator because the adjoint of anything is a closed operator. So that's actually a proof that H1 is complete. It must be complete because this is a closed operator. Now we could take this operator and take its adjoint back again. So we started with a t, we got a t star, but t star star will not be this operator because this is not a closed operator. Because there's nothing that says if you have a sequence of C0 infinity functions, their convergence, their divergence is converging, that the resulting function is still C infinity. It's not true. Okay, so now we could take the adjoint of grad. So grad with the domain H1. And what do we get? Well, you write down the same kind of reasoning. Well, so then, what letters am I using? If I take a W is in the adjoint of grad, that means that W dot the gradient of U integrated is equal to some function times there exists some function z such that this is equal to wz. This is equal to z u. So w is in the adjoint of grad and grad star w equals z in L2. That would be this equation. So now when you integrate by parts over here, now there's going to be, now you have to bring in the traces on Sobolev spaces, and this is going to be the integral of minus div w dot u plus the integral over the boundary of w dot nu. So now we're using a little more analysis. We have to prove the trace theorem on a Sobolev space that says there exists a trace of these functions. And so the conclusion is that this equation would hold if z is minus div w and the trace of w dot n is 0. Okay, so the adjoint of grad is minus div, but with the domain h0 div, which is defined to be the set of w whose divergence is in L2, such that w dot n equals 0 on the boundary. Okay, so that's how we would look at the gradient and the divergence. Well, the gradient as a bounded, as a closed unbounded operator, and its adjoint is the divergence, which is also a closed unbounded operator. But its divergence has this domain h0 div. Okay, and what about whether these operators have closed range? So let's ask this question. Is the range of the gradient, is the gradient of h1 closed in L2? Well, we have the closed range theorem, which would ask the same question for minus div. Is minus div of h0 div closed in L2? The answers are the same because of the closed range theorem. An operator is closed if and only if its adjoint is closed. This one you probably know if you think about it. You can take any function and write it as the divergence of a function. And the only condition to be able to satisfy boundary conditions. So how would you do it? Suppose I'm given a function f, and I want to write f as the divergence of some w. And I want w dot n is 0 on the boundary. Well, I could solve the Laplace equation. Laplace c is equal to f, dc dn is equal to 0 on the boundary. And I could let w be gradient of c. And the only condition is that f have integral 0, so I can solve the Neumann problem. So if the integral of f equals 0, then f equals div w for some w in h0 div. Okay, and the reason I point that out is that means that the range of the divergence is finite codimensional. Only it's one codimensional. So range of div, well, so I'll write that as div of h0 div is finite codimensional, one codimensional actually, which implies that it's closed. That was one of the theorems that was easy to carry over for closed operators, that finite codimension of the range means it's closed range. So it's closed in L2, and that's if and only if grad of H1, its adjoint, is closed in L2. So the conclusion from all that is that if we take the domain, if we take the gradient with domain H1 as an unbounded operator, it's closed, densely defined, closed range. Now we can do this for all the operators. We can do it for div with domain H div, curl with domain H curl, and so forth. So these are all nice, closed, densely defined, closed range operators. There's curl. I'm going to skip it. And so I think I will end the story there. What's that?
Start changing the domain of your operator.
Change the domain of the operator. Well, you get different operators. So if you take a differential operator, linear differential operator, and you take its domain as functions without any boundary conditions, then typically the adjoint will be the formal adjoint with boundary conditions. So the domain of gradient on all of H1 is minus divergence, the adjoint minus divergence on H0 div. The domain of gradient on H01 would be minus divergence on all of H div. And you can use the integration by parts formula, Stokes' theorem, to figure out what boundary conditions will come up in the range. This requires, to do it right, that you prove trace theorems that make those things valid. Okay, and as long as, and you could choose other things, you know, you could choose, for example, as the domain of gradient, those functions in H1 that are 0 on half of the boundary. The adjoint would be divergence three things whose normal derivative vanishes on the other half of the boundary. And okay. Yes. Yes.
But what is the computation of the Betty number for the Dirac complex?
Okay, did everybody hear the question? The question was that I said the Betty numbers, which is the dimension of the homology groups for the simplicial complex, I gave a physical meaning, number of holes and voids and so forth. And what is the meaning of the Betty numbers of the Dirac complex? And the key point is that the cohomology of the simplicial complex is isomorphic to the cohomology of the Dirac complex by the Dirac mass. So they're exactly the same. There are no different Betty numbers for the Dirac complex, for the simplicial complex. They're the same numbers. So there are two different ways you can compute the same numbers. So I take a domain, so I take a donut, and it has first Betty number 1, unless it's a jelly donut with a gap in the middle, in which case, well, yeah, it still has first Betty number 1, I guess. And I can compute that in different ways. I could triangulate that thing, and I could put down the incidence matrices that compute the boundary, and I could look at their ranges and null spaces and compute the quotients, and I'll get that Betty number 1. Or I could set up some PDEs. I could set up the PDE curl u equals 0 on that donut, and u is equal to gradient of phi on that donut, and find out how many side conditions I need to solve that PDE, and how much non-uniqueness I have to those PDEs, and I could take that quotient, and that would be the same number 1, but computed in a different way. So for the Betty number k, according to Dirac, is the null space of the operator dk from k forms to k plus 1 forms, modded out by the range of the operator dk minus 1 from k minus 1 forms to k forms. The Betti number of the simplicial complex is let me do the homology version because it's equal to the cohomology one. So that would be the null space of the boundary operator from k chains to k minus 1 chains, modded out by the range of the boundary operator from k plus 1 chains to k chains. Now these are certain numbers. These numbers are associated to the domain omega, and they're the same number. That number can be computed this way, or it can be computed this way. They're very different computations, but they give the same answer. Okay, so there is no Betti number of the de Rham complex. There's a Betti number of the domain, which can be computed by computing the cohomology of the de Rham complex. Any other questions? Yes, I will, if you leave me alone, I will go to talk to Lauren and see if she can post it. And I think what I'll do is I'll post them as soon as I finish them, because the ones in the future may get changed. By the way, if you see any errors, typos, something's unclear or something like that, I'm open, like suggestions. And I did commit to write this all up. That'll probably take another year or so, but I hope to have this all written up in a nice form. Okay, thank you.